Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss the solution of linear differential equation with constant coefficients. Consider first the linear differential equation with constant coefficient in which RHS side equal to 0. That is d raised to ny by dx raised to n plus p1 d raised to n minus 1y by dx raised to n minus 1 plus p2 d raised to n minus 2y by dx raised to n minus 2 plus dash 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 plus up to pny equal to 0. Denote this equation as equation 1. That means this equation can also be written in the form fd of y equal to 0. Here p1, p2, pn are constants. Consider the case 1. In case 1, we discuss that the roots are real and non-repeated of equation 1. Here we consider equation 1, that is fd of y equal to 0. Let y equal to e raised to mx be solution of this equation 1. Hence, if we put y equal to e raised to mx, then this equation 1 must be satisfied. Hence, fd of y means e raised to mx, and into bracket d raised to n of e raised to mx is m raised to n of y, that is m raised to n of e raised to mx plus p1 d raised to n minus 1 of e raised to mx by dx raised to n minus 1 is m raised to n minus 1 p1 as it is plus d raised to n minus 2 by dx raised to n minus 2 of e raised to mx is m raised to n minus 2 p2 as it is plus up to pn. Operator on y, that is e raised to mx equal to 0. Hence, auxiliary equation is bracket equal to 0, that is m raised to n plus p1 m raised to n minus 1 plus p2 m raised to n minus 2 plus up to pn equal to 0. This equation is known as auxiliary equation of equation 1. Let m1, m2, mn be n real non-repeated roots of equation 2. Hence y equal to e raised to m1x, y equal to e raised to m2x, comma y equal to e raised to m3x, comma dash 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 y equal to e raised to mnx are solutions of equation 1. Hence, complete solution of equation 1 is y equal to c1 e raised to m1x plus c2 e raised to m2x plus c3 e raised to m3x plus dash 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 plus cn e raised to mnx. Denote this as equation 3, where m1, m2, m3 up to mn are roots of auxiliary equation. That means all the roots m1, m2, mn are distinct, they are real and they are non-repeated, and solution of this equation 1 is y equal to c1 e raised to m1x plus c2 e raised to m2x plus c3 e raised to m3x plus dash 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 plus cn e raised to mnx. This is solution of equation 1 in which roots are real, and non-repeated. Now we consider case 2. In case 2, the roots are, we discuss that roots of equation 1 are repeated. Let the root m1 of the auxiliary equation is repeated twice. Then the general solution 3, that is we denote this as solution as 3, then this when m1 is repeated twice, then this general solution 3 becomes y equal to in bracket c1 plus c2 bracket complete into e raised to m1x, since m1 is repeated 2 times, plus c3 e raised to m3x plus dash 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 plus cn e raised to mnx. Hence y equal to a e raised to m1x plus c3 e raised to m3x plus dash 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 plus cn e raised to mnx, since a equal to c1 plus c2. See. But this solution contains n minus 1 arbitrary constants and order of equation 1 is n. Hence, this is not the general solution of equation 1. To find the general solution, we proceed as follows. As the root m1 is repeated twice, so fd can be written in the form of d minus m1 bracket square into phi of d. Hence, the solution of in bracket d minus m1 bracket complete bracket square into y equal to 0 is also solution of fd of y equal to 0. Now consider is in bracket d minus m1 bracket complete bracket square into y equal to 0. That is d minus m1 into d minus m1 of y equal to 0. Denote this as number 4. Let d minus m1 in bracket d minus m1 bracket complete into y equal to u. Denote this as 5. Then this equation 4 becomes d min in bracket d minus m1 into u, since d minus m1 into y equal to u equal to 0. That is d minus m1 into u equal to 0. That is du by dx minus m1u equal to 0. But this is linear differential equation and hence we can solve it as also by separating the variables. That is du upon u minus m1 dx equal to 0. Integrating we get log of u equal to m1x plus c. That is u equal to c1 e raised to m1x, where c1 is arbitrary constant. Hence, equation 5 becomes, equation 5 means d minus m1 of y equal to u. That is d minus m1 of y equal to u is c1 e raised to m1x. That is dy by dx minus m1y equal to c1 e raised to m1x. This is linear differential equation of the type dy by dx plus py equal to q. And to solve linear differential equation, we first find integrating factor, that is e raised to integral p dx. And solution of this linear differential equation is y into integrating factor equal to c plus integration of integrating factor into q dx. Using this formula, we first find integrating factor, that is e raised to integral p. P means minus m1 dx, which is equal to e raised to minus m1 x. Hence, solution of this linear equation is y into integrating factor is e raised to minus m1x equal to c2 plus integration of c1 e raised to m1x, that is RHS side cube, into integrating factor is e raised to minus m1 x into dx. Simplifying, we get here e raised to m1x, e raised to minus m1x cancels with each other. So we get y into e raised to m1x equal to c2 plus c1 into integration of dx. It is, we get this is equal to c2 plus c1x. Thus, y into e raised to minus m1x equal to c1x plus c2. Hence, multiplying by e raised to m1x, we get y equal to in bracket c1x plus c2 bracket complete into e raised to m1x, which is the general solution of 4. That is, if similarly if m1 is repeated 3 times, then similarly if this root m1 is repeated 3 times, then we get solution as y equal to c1x square plus c2x plus c3 bracket complete into e raised to m1x. When roots are repeated 3 times, here c3. When roots are m1 root is repeated 2 times, here c2. Here m1 is repeated 3 times, so here constant is c3. And when m1 is repeated 2 times, constant is c2 and power of x is less than 1. That is, m1 is repeated 2 times, so power is 2 minus 1, that is 1. Here m1 root is repeated 3 times, so power of x, highest power of x is 3 minus 1, that is 2. Similarly, in general we can write, if the root m1 is repeated n times, then the corresponding solution is y equal to, if the root m1 is repeated k times, then the highest power of x must be less than 1, that is k minus 1. c1 x raised to k minus 1 plus c2 x raised to k minus 2 plus up to ck bracket complete into e raised to m1x. Now we consider case 3. Here we discuss that roots of equation 1 are complex. In case 1 we discuss the roots are real and non-repeated. In case 2 we discuss the roots are repeated, and in case 3 we consider that the roots are complex. Here we assume that let alpha plus I beta and alpha minus I beta be the complex roots of the auxiliary equation 2. Then the corresponding part of solution is y equal to, here there are two roots, alpha plus I beta and alpha minus I beta. So corresponding part of solution is y equal to c1 e raised to in bracket alpha plus I beta bracket complete into x plus c2 e raised to in bracket alpha minus I beta into x. This is equal to e raised to alpha x into bracket c1 e raised to I beta x plus c2 e raised to minus I beta x bracket complete. Hence y equal to e raised to alpha x into bracket c1 cos of beta x plus I sin beta x plus c2 cos of beta x minus I sin beta x, since e raised to I theta equal to cos theta plus I sin theta. Using this formula, we get here coefficient of I is beta x, so that we get c1 cos of beta x plus I sin beta x plus c2 cos of beta x minus sin of beta x for minus sign. Here minus sign is there. Hence y equal to e raised to alpha x into bracket c1 plus in bracket c1 plus c2 bracket complete into cos of beta x plus I into bracket c1 minus c2 bracket complete into sin of beta x bracket complete. Hence y equal to e raised to alpha x into bracket a cos of beta x plus b sin of beta x, that is c1 plus c2 equal to ac and I into c1 minus c2 equal to bc. Thus, when the roots are complex, that is alpha plus minus I beta are roots of the auxiliary equation, then the corresponding part of solution is y equal to e raised to alpha x into bracket a cos of beta x plus b sin of beta x. Now we consider one remark. If the roots are repeated, it means if this complex root alpha plus minus I beta are repeated, then the corresponding part of solution is y equal to in bracket c1 plus c2x bracket complete e raised to in bracket alpha plus I beta bracket complete into x plus in bracket c3 plus c4x bracket complete e raised to in bracket alpha minus I beta bracket complete into x. This can be written as y equal to e raised to alpha x into bracket in bracket a1 plus a2x bracket complete into cos of beta x plus in bracket b1 plus b2x bracket complete into sin of beta x. This is the solution when the complex roots alpha plus minus I beta are repeated 2 times. Thus we have discussed all the 3 cases when the roots are real non-repeated, when the roots are repeated, and when the roots are complex. Thank you.